pamozi ndi mtima umo. Tiende 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 pamozi ndi mtima umo.
Good afternoon, viewers. Welcome back to the MTN Teleschool. This is another session of the physics revision. My names again are James Kabuye. We'll go through these questions with you together as we revise. So this is 2016 Pure Physics Paper 2. I begin reading the questions. Question 1. Figure 1.1 below shows how a vernier caliper indicating a measurement can be used. So that figure is shown there, and they're saying question A part 1, which jaw, A or B, can be used to measure the thickness of a wire nail? So we have the two jaws. So the jaws labeled A are used for measuring internal diameters of objects, while the jaws represented by B, they are used to measure external diameters of objects. So the thickness there is referring to the external diameter of the object. Therefore, jaws labeled B will be the most appropriate. Part 2. Explain the function of the vernier scale in this instrument. Let me just take you to this small diagram I have here, which shows the vernier calipers, the major portions of the vernier calipers. And let me just remove these unnecessary things. When we look at this diagram, what we are saying is that we have dealt with jaws A and B. Now they are saying explain the function of the vernier scale, this smaller scale here. The function of that smaller scale is to give us the second decimal place in centimeters. The second decimal place in centimeters. As we can see, the uppermost scale can only give us one decimal place. So the second decimal place is going to be given by the vernier scale. Part 3. What is the reading indicated in the diagram? Let's check again on my small drawing here. When we check this very closely, we must make sure that we notice and identify where the smaller scale starts from, where the vernier scale starts from. In this case, this is the vernier scale I'm referring to. You must know where the zero mark is located, this zero mark. When it's located, it tells you exactly where you must stop reading from in as far as the main scale is concerned. So, where 0 is here. When you look at this, you find that this is 0.5, 0.6, 7, 8, 9, 1, 1.5, 1.2, 1.3, 1.4. So at 1.4, the 0 is indicating the position where exactly the vernier scale starts. So you stop there and then you indicate 1.40 centimeters as the actual reading on the main scale. Then you say plus Since we said that the vernier scale is going to give us the value of the second decimal place, the figure that is on the second decimal place, then we simply quickly check, how do we get it now, the second place? We must go for a line on the vernier scale that coincides with any other line on the main scale. To coincide means to look like they are in a straight line. These two lines must look like they are in a straight line, if not to be in a straight line. So you check out of these. Let's look at this vernier scale. We check on position 5, and when we check on position number 6, from the diagram that has been drawn, you may realize that number 6 actually seems to be in a straight line. Line number 6 is going in the straight line with the top one, and so that gives us 0.06 centimeters. So that the total reading becomes 1.46 centimeters. I want to repeat this. The second decimal place has been found by the 6th demarcation, which seems to be in a straight line with the line that is above on the main scale here. Okay, we move on. Okay, we'll move on. In the space below, draw a section of a micrometer screw gauge, the sleeve and the thimble sections, showing a measurement of 4.35 millimeters. This is a measurement which they want us to show on the micrometer screw gauge. So we ignore the rest of the parts of the micrometer screw gauge, which are not very critical. We just draw the ones that are being asked for, where the readings are. So join me in this drawing. I'm going to draw the sleeve and the thimble. This is my middle line. I'm going to put 0 here. I'm going to put 1, 2, 3, 4. Okay, that is my sleeve. 1, 2, 3, 4. Okay, after that, then I can draw my thimble like that. Then now I can even join these ones, these parts. Now notice that this is 1, 2, 3, 4. Under we have subdivisions of 0.5s here. Okay, remember that I'm very cautious. I'm not going to put any division just before the thimble, so that the other next two readings, the next figure is going to be found on the thimble. Let me go to the thimble now and put 30 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 35, 36, 37, 38, 39, 40. So you can see that the line that I've put on 35 coincides with the line that is on the sleeve. So that tells us that now the figure is here on the sleeve 4.00 millimeters plus 0.35 millimeters, so that the total becomes 4.35 millimeters. This is the reading that is needed. Move on to part 2. If the spindle of a micrometer screw gauge moves through 0.5 millimeters for each complete turn, what will be the pitch of the screw? the pitch of the screw will also have will be seen to be 0.5 millimeters. The pitch will be 0.5 millimeters. Part 3. Part 3. The question says, when a micrometer screw gauge is zeroed, the spindle and the slip surfaces start with a reading of 0.25 millimeters. 0.25 millimeters. These are showing when the two surfaces meet. What is the actual measurement of the diameter of the ball bearing? Measured to be 3.05 millimeters by the micrometer screw gauge. Here what we must understand is that there is obviously a zero error. You know, a zero error is a figure that is shown when you close the jaws, or you close the spindle and the envelope of the micrometer screw gauge, and you don't see 00 being seen on the micrometer screw gauge. It means that it has a zero error. So you must take note of that. Either you go through the process of zeroing it by adjusting the screw behind the micrometer screw gauge, or you simply take note of that zero error, which can either be positive or can be negative. In this case, we have a figure which is 0.25 millimeters showing when the spindle and the envelope are holding each other without anything inside. So that should be a figure that should be subtracted from the total figure when we do actually put an object in between the envelope and the spindle. In this case now, the actual reading becomes 3.05 millimeters minus the one that was showing already, which is 0.25 millimeters. So that the actual reading is actually 2.80 millimeters. We move on to the next question. Why would one opt to use a micrometer screw gauge compared to a vernier calipers in determining how thick a quarter knot is? I want to take you back, viewers, to the first question that we had in paper 1 of 2016, where it was actually asking about the most appropriate measuring instrument that we can use to determine the thickness of a knot. And we were saying that accuracy is very, very critical in that it tells you how many decimal places an instrument can give you, and therefore how close the value you are getting is to the actual that we are looking for. So if the number of decimal places from an instrument are actually more, then it means that it gives a value that is very close to what we are looking for. So we say that such an instrument is very accurate. In this particular case, therefore, you find that in the attempt to use vernier calipers or indeed a micrometer screw gauge, a micrometer screw gauge in millimeters can give us a maximum of 2 decimal places, and in centimeters can give us a maximum of 3 decimal places. While a vernier calipers in millimeters can only give us 1 decimal place, and yet in centimeters can only give us 2 decimal places. And therefore, from here it shows that a micrometer screw gauge is more accurate than a vernier calipers. We move on to question 2. The figure below shows the motion of a body of mass, let me take note, of mass 6 times 10 to the power 5 kgs. 6.0 times 10 to the power 5 kgs. That is the mass of the object. The total frictional force acting on the body is 0.5. Frictional force is 0.5 times 10 to the power of 6 newtons. So viewers, we have the mass and we have the frictional force, and the motion of this this body has been shown in form of a graph. I hope you are able to see that graph. But anyway, let me just look at this graph very quickly and have it done here very quickly. This is the graph that is going to depict the motion of that body. Okay. Now, when we look at this graph, viewers, the question says, calculate the acceleration of the body in the first 4 seconds. This is the region where we are interested in. First 4 seconds. So, it means that we can say that, allow me to close this, and say that acceleration is equal to final velocity minus initial divided by t. The final velocity is 40, initial is 0, time is 4. So the acceleration is actually 40 divided by 4, which is 10 meters per second squared. That is the acceleration. Now, the other way to work it out is to say it's the change in the y divided by the change in the x. What is the change in the y? Y is changing from 0 to 40. So 40 minus 0 is the change in the y. And then the change in the x is changing from 0 to 4, so the change is 4 minus 0. So that we get 40 out of 4, which still gives us 10 meters per second squared. Viewers, this is the acceleration which is being asked for. We move on. What is the total distance traveled by the body in 10 seconds? We go back to this question. And this is the graph. Allow me to rub some things here. Right? Now, we must look at the whole graph in totality. So they are saying in 10 seconds. Okay, 10 seconds is up to here. So we are going to make sure that we identify the space that is being considered. The area under this graph will tell us the distance that was covered in 10 seconds. So, we can divide this into portions of a triangle A and a rectangle B. So, the area, the total area for these two portions will tell us the distance traveled. So, first distance is half base times height, half the base, which is 4 seconds, times beg your pardon, times the area of the rectangle, which is times the height, which is 40 meters per second. So you find that S and S will cancel. 2 and 2 there will be 2 and 4 there will be 2. The total is 8 meters just for that triangle. And then we move on to the other part, which is S is equal to L times B. There L is from 4 to 10, which is 6, and then we can use that to be 40. When we multiply this 6 times 40, we get 240. So the total distance traveled, total distance means 240 meters plus 80 meters. That means we get 320 meters, right? 320 meters as the total distance traveled. That is from 240 plus 80, which gives us 320 meters. We move on. Calculate the net force acting on the body in the first 4 seconds. It is the net force that gave us the acceleration that we have found. So, it's not anything else, it's the net force. So, the net force is as good as saying a resultant force. It's the resultant force that actually gave us this acceleration. So, resultant force is equal to ma. And then, we can say that the mass is actually 6.0 times 10 to the power 5 times the acceleration which we got as 10 meters per second squared, and all this will give us newtons at the end, so that we get 6.0 times 10 to the power 6 newtons. That is the net force that is acting on this body. Part D, what is the force exerted by the engine on the body in the first 4 seconds? Oh, interesting question. We found the net force in the previous question, so it means that the engine must provide a force greater than the net force. There should be a total force such that it defeats the frictional force and also provides an extra force which must generate an acceleration. In that case, therefore, we say engine force should be equal to 6.0 times 10 to the power 6 plus the frictional force, which was 0.5 times 10 to the power 6, and so that the total becomes 6.5 times 10 to the power 6 newtons. That is the force that must be provided by the engine in order for this acceleration to occur. Next question, question 3. A learner set up an experiment to determine the density of an insoluble substance, X. She used a spring, scale pan with a pointer, a 20-gram standard mass, and a half-meter rule. Figure 3.1 below shows how the apparatus was arranged. So we can see that diagram, viewers, and what we notice is that the pointer is on 30, okay, and then when the 20-gram mass was added to the pan, the pointer rested on the 20 centimeter mark. Okay, so it means that after inserting the 20-gram mass, the pointer moves. The pointer was here on 30, now it is pointing on 20. So we can get the extension due to the load. What is this extension now? Extension means 30 minus 20, all right, so that we get 10 centimeters. So basically the spring extended by 10 centimeters after having been inflicted with a load of about 20 grams. Now, let's go to the questions. The first question is define density. Define density. Density is defined as the mass per unit volume of a substance. How much mass is acting per unit volume of a substance? You can mention like that, or you can simply write density is equal to mass over volume. You must take care that you do not use symbols. If you are not going to describe density and define it as mass per unit volume of a substance, then you can say density is equal to mass over volume, where mass must be written in words and volume must be in words, and never the symbols. That is the definition of density. Mass that is acting per unit volume of a substance. What is the mass of the substance X? Now, they are saying that when substance X was added to the scale pan with the 20-gram mass on it, the pointer moved to the 5 centimeter mark. Now, the meaning is that, if we go back to this diagram, now the pointer has come to 5 centimeters. The meaning is that, therefore, having added X, now the extension is 30 minus 5, which gives us 25 centimeters. That is the new extension. So, now we must find the total mass that caused this extension. 20 grams caused an extension of 10 centimeters. X grams must cause an extension of 25 centimeters. When we cross multiply and manipulate these figures, what we see is that X should be equal to 20 times 25 divided by 10. So, you are going to find that this 0 cancels. 2 times 25 is 50, and so we have 50 grams as the new mass. Now, that is not the mass of substance X. It is the total mass of the 20 grams plus the mass of X. Therefore, mass of X, let me put it this way, mass of X should be equal to 50 minus 20, which gives us 30 grams. That is now the mass that we are being asked to find. Part C, part 1. Briefly describe how the volume of the substance X can be determined. Substance X, we are told that it's insoluble. What it means basically is that it does not dissolve in water. So we can put it and slide it into the water and it will not dissolve. So there are two methods we can do that. First, we get a measuring cylinder if we wish. We can get a measuring cylinder. We put a known volume of water in that measuring cylinder. Then we record it as V1. Then we can insert substance X inside here so that the volume now increases to V2. Okay? When that has happened, then we can notice that the volume of the substance X is V2 minus V1. That is how we can get the volume of that substance. If we don't do that, if we find that this substance is a solid substance such as a stone, an irregular stone, which cannot fit into the mouth of a measuring cylinder, then we can use a displacement cane, or it's popularly called the Eureka cane. We do it this way. We put this Eureka cane on a surface such as this, and this is our Eureka cane. Okay, and under here we put our measuring cylinder and we put some water there. Then we lower that substance inside here. What will happen is that some bit of water will come out up to some level V, and that V is the volume of X. That will be the volume of X. Volume of X. Okay, straight away in cubic centimeters. This is method A, this is method B. We move on. Given that the volume of substance X is 0.01 dm cubed, find the density of substance X. Take 1 dm cubed to be 1,000 cubic centimeters. All right, so we must find the volume in cubic centimeters. So we say volume is equal to 0.01 times 1,000. so that we get 10 cubic centimeters. This becomes our volume of this substance. For accuracy's sake, you can put decimals, but I think let's leave it as it is. Now, if this is the volume of the X, they are saying that we must find the density. Density is mass over volume. If you want to be more scientific, you can use the symbol for density, a Greek letter, a rho. This letter indicates the symbol for density, so you can say mass over volume. So the mass we already found it 30 grams. The volume now we have found it is to be 10 cubic centimeters. So then the density is 3.0 grams per cubic centimeter. Okay? We move on to the next part of the question, part 3. Calculate the relative density of a substance X. The word relative density refers to the mass of a certain volume of a substance divided by the mass of an equal volume of water. What it means basically is that we must get a certain volume of a substance and we find the mass, and we make sure that we get the same volume of water and we get the mass of that. Then when we divide these two, we'll get the relative density. So, I will say relative density is equal to mass of some volume of a substance divided by the mass of an equal volume of water. So that we say, in this case, we got 10 cubic centimeters of this substance and we found 30 grams. Now we are going to get 10 cubic centimeters of water and see what the mass is. We must understand very quickly that the density of water is actually 1 gram per cubic centimeter. It means that every cubic centimeter of water weighs 1 gram. So if we have 10 mils, 10 cubic centimeters of water, then we should have 10 grams. So that relative density now, gram and gram will cancel. We get 3.0 as relative density. No units, because relative density has no units. The grams are cancelling. We move on to the next question, question 4. The figure shows a car of mass 1 ton moving on a level road. The total driving force of the car and the frictional force opposing its motion are 3,000 newtons and 1,000 newtons respectively. And the car has been drawn and has been shown in the diagram, as you can see, dear viewers. Now, the questions start. Calculate the acceleration of the car. Let me write something very quickly here. Okay, dear viewers, before we calculate this particular interesting problem, let's go for a break, and I meet you shortly after this break. Thank you.
Without music, our lives would be lifeless.
Music gives the mind wings.
Music refreshes the soul on this journey of life and never dies. It's who we are. I mean, it's what we do.
It's what we feel.
What would we be without music?
music streaming is MTN Music Plus.
MTN, everywhere you go.
Do you expect more from your internet service? Maybe it's time to switch to MTN's 4G internet. Introducing the next level in high-performance mobile network technology, taking your home or office internet experience to a whole new level while keeping it simple. Get to work by the click of a button or manage your team from miles away. Browse faster, download multiple files, and stream videos quicker with no limits. Get it all done with MTN's 4G internet. So don't let your internet slow you down. Stay online in real time all the time. Get your MTN 4G SIM today and find your nearest 4G zone to enjoy maximum performance of your 4G enabled device. MTN, everywhere you go.
Welcome back, viewers, from our short break. Thank you so much, Kennedy, Chete, Boniface Zulu, and others for watching the MTN Teleschool. Thank you so much. Continue to be with us on this particular program. My humble feeling is that you continue to be with us until the end. Thank you. We move on to question 4. The question says the figure shows a car of mass 1 ton moving on a level road. The total driving force of the car and the frictional force opposing its motion are 3,000 newtons and 1,000 newtons respectively. The diagram shows clearly this car, and the question says calculate the acceleration of the car. Let me draw something here so that you see. I want to draw something here very quickly so that you see. Okay, thank you. So this is the situation, and we have this as our car, and it's moving this way. The force F, I can call it F2, which is 3,000 newtons. I also have friction, which is opposing the motion, 1,000 newtons going this way. So please understand what is happening now. The force is pulling this way, and this I'll call it F1. So the frictional force, I'll call it F1. The engine force and every other force pushing it forward, I'll call it F2. So they are saying calculate the acceleration of the car. We must make sure that before we calculate anything, we must find the resultant force, because it is the resultant force that produces an acceleration. Without a resultant force, there can be no acceleration. As long as the resultant force on a body is 0, then the body continues in its state of rest if it is at rest, or continues in its state of motion if it is moving at a certain speed and maintains that. So in this case, we must find the resultant force, which I'll call Fr, which will be F2 minus F1. That means 3,000 minus 1,000. Because 1,000 is opposing, so we get 2,000 newtons as the resultant force. But the question is not about the resultant force, it's about the acceleration. So force is equal to ma, where m is the mass, a is the acceleration. So acceleration therefore is force over m. So we have 2,000 divided by the mass, which is, we are told 1 ton, which we must convert to kgs, and it will be 1,000 kgs. So we put 1,000 kgs here, so that we get 2 meters per second squared as the acceleration of the car. We proceed to the next question. If the car started from rest, calculate the kinetic energy gained by the car in 10 seconds. Okay, right. Let's do this. Final velocity is equal to u plus at. We don't know the final velocity after 10 seconds, so we must find it. So the initial is 0 because it's coming from rest. Acceleration is 2 and time is 10. So it means that the final velocity after 10 seconds is 20 meters per second. So now that we know the speed at which it's moving 10 seconds after the motion, we can find the kinetic energy. Kinetic energy will be equal to half mv squared, where m is the mass, v is the velocity. So half of the mass, which is 1000, times the velocity, which is 20, times 20. So that we get 2 into there, then we get there 10, and we are going to get 1000000. That means that we are saying that, those are the joules that we have, which is 1.0 times 10 to the power 1, 2, 3, 4, 5 joules. All right. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Fine. That is the kinetic energy after 10 seconds. The power developed by the car engine in 10 seconds. The power is the rate at which work is done. The power is the rate at which work is done. So, the work that has been done is already found. So, what we can do is simply to divide the power by the time, and then we'll be able to get, we divide the energy by the time, and then we'll be able to get the power. So, when we divide 1.0 times 10 to the power 5 divided by 10, we are going to get 1.0 times 10 to the power 4 watts. That will be the power. We go on a short break, and as soon as we come back, we'll proceed with the other questions. Thank you.
Without music, our lives would be lifeless.
Music gives the mind wings.
Music refreshes the soul on this journey of life and never dies. It's who we are. I mean, it's what we do.
It's what we feel.
What would we be without music?
The future of music streaming is MTN Music Plus.
MTN. Everywhere you go.
I told the bus driver that I work hard for my money, so it better gets to Chipata.
Yeah, that's right. That's what I told him.
Yeah.
Weather, drama nizingono, or nizambili.
Tituma. And he kept trying to tell us something, but I was like, Ukagamba, Tilo.
Cause cash money yave across Zambia.
Tituma. At bus and Kuchpat. The end of South Africa. Hello, what?
Run, K-Star, run! You got the bus.
Sending money doesn't have to be this dramatic. Open an MTN mobile money account today and send money to friends and loved ones across Zambia instantly. Dial *303# to send money with MTN, Zambia's #1 network. With MTN mobile money, Tituma.
MTN. Everywhere you go.
Rise up this morning, smile with the rising sun. 3 little birds pitch by my doorstep, singing sweet songs, our melodies pure and true, saying, this is my message to you. Singing, don't worry about a thing, It's gonna be alright. Cause every little thing is gonna be alright.
How you use your data is up to you. With the widest network coverage, it's amazing what you can do on MTN.
This is my message to you.
Hello! This is all you need to know about data bundles. Like when you need airtime to make calls, you need data bundles to browse the internet, send and receive photos on Facebook, chat on WhatsApp, send emails, listen to music, and many other things. Data is measured in bytes, kilobytes, megabytes, and gigabytes. These are a bit like money, and just like your bank balance, your MTN account has a data balance that you can use to buy data bundles ranging from 5 megabytes to 20 gigabytes for daily, weekly, and monthly subscription. To buy a bundle, dial *335*1#.
From sending emails to browsing or watching online videos, many of the things you use depend on your device's functionality and network capability. Entry-level devices have limited data usage, whereas smartphones and computers have limitless data usage. The longer you spend online, the more data you use.
Sometimes you feel like your data is running out really fast. That's because today's modern technology and higher definition content require and use up a lot more data. No need to worry. Data can be managed to work for you by minimizing on the number of apps that automatically update themselves and turning off your data when not in use. Make sure you use data bundles to browse the internet. When your bundle is depleted, you will be billed from your airtime. Perform regular data balance inquiries by dialing *335*3#.
I told the bus driver that I work hard for my money, so it better gets to Chipata.
Yeah, that's right. That's what I told him.
Yeah.
Whether drama is ngono or nizambili
Tituma. And he kept trying to tell us something, but I was like, Ukagamba, Tilo.
Cause cash money yeve across Zambia.
Tituma. At bus and Kuchpat. The end of South Africa. Hello, what?
Run, K-Star, run! Don't cut the bus.
Sending money doesn't have to be this dramatic. Open an MTN mobile money account today and send money to friends and loved ones across Zambia instantly. Dial *303# to send money with MTN, Zambia's #1 network. With MTN mobile money, Tituma.
MTN, everywhere you go.
Welcome back, viewers, to the physics session on the MTN Teleschool. We go back to our question that we were dealing with just before we went for break. We didn't finish it because we were supposed to multiply some things by a certain figure, so we go back to that. The first, let me just start with A. Question 4A. We said that acceleration should be equal to force over m, so that the force was 2000 divided by the mass, which was 1000. So acceleration was 2 meters per second squared. Auto save, eh? Yeah, better. Right, so we continue from there and continue with this question. Part B was, before we went for break, if the car started from rest, calculate the kinetic energy gained by the car in 10 seconds. I think that was the question. So we said we don't know the final velocity, so we must find it. Final velocity is equal to u plus at. So u was 0, acceleration was 2, time was 10. So after 10 seconds, it was moving at 20 meters per second. So that we said, therefore, kinetic energy was equal to half mv squared. So half times 1000 times 20 times 20. So that when we cancel out this, we get 10. We are going to get 2 and 2,000,00 joules. This is what we must get, which is 2.0 times 10 to the power 1, 2, 3, 4, 5 joules. This is the kinetic energy that we should have gotten just before that minor break came in. We move on. The power developed by the car engine in 10 seconds. Power, I said, that is the rate at which work is done, and so the work is seen in form of the gain in the kinetic energy that was seen after the car moved for that period of time, 10 seconds. So the whole work done is seen in form of the gain in the kinetic energy. So we can't again begin to work that out, that work. So what we do is we say the work done is equal to kinetic energy gained, which should be equal to 2.0 times 10 to the power 5 joules. So now power is work done over time taken. We didn't finish this question before we went for the break. So work done now is 2.0 times 10 to the power 5 divided by time, which is 10 seconds. So we are going to get 2.0 times 10 to the power 4 watts. Okay, let me just write it properly. Let me just write it properly, which is 2.0 times 10 to the power 4 watts. Okay. Okay, that is the power. We move on to question 5. Are these mystical? Oh, sorry. Right. Question 5. Elena poured 100 cubic centimeters of water in beaker S and 100 cubic centimeters of water in beaker T. Beaker S was kept at 40 degrees C and beaker T was kept at 80 degrees C in the same part of the room. Figure 5.1 shows the two beakers after 3 days. Viewers, I appreciate your viewing. Please continue following this program. Do not call. I've seen calls coming. Do not call. Just text or you just comment straight. Okay, the diagrams have been seen there, and the first question says, explain why more water evaporates when water is kept at 80 degrees C. We are looking at the kinetic theory of matter, which says that matter is made up of particles that are in a continuous state of random motion. And this random motion is dependent on the energy content. So the more the energy, the more the motion. So what it is that basically the water at 80 degrees C has more energy than water that is at 40 degrees C. That's the reason more water evaporates from the other one that is at 80 degrees C than the other one that is at 40 degrees C. There is more energy there, and so more molecules are finding it easy to escape the forces of attraction, and so they are going into the space. Apart from an increase in temperature, state one change that causes water to evaporate faster. We can increase the surface area. Wind also can cause an increase in the evaporation. So these two are very, very critical in terms of the rate of evaporation. It's also noted that humidity is also very critical. It affects the rate of evaporation, because when the air around and above the dish in which the liquid is saturated with vapor, then evaporation does not get to be encouraged to take place, because that space is already saturated, so evaporation is suffocated, if you like. We move on to part B. The following information was collected and recorded during an experiment to determine the specific heat capacity of water. Heater rating 60 watts, 12 watts. So power is 60 watts and 12 volts. That is the data. And then we do have mass of water, which is 200 grams, which is 0.2 kgs. Initial water temperature is 20 degrees C. Final temperature of water, T final, 48.2 degrees C. Time taken for this water to be heated, 10 minutes times 60 seconds, which would give us 600 seconds. Okay, we must always take these values to correct and appropriate units. And so we move on. The question says, calculate the specific heat capacity of water from the data collected. The quantity of heat that water absorbed was equal to the mass times the specific heat capacity times the change in the temperature. This is the change in the temperature, where we say T final minus T initial. So the change in the temperature is actually 48.2 minus 20, which gives us 28.2. This is the change in temperature, 28.2 degrees C. These are the degrees. So we can go on and say the mass of water is, actually you can notice very quickly also that this quantity of energy can also be found by multiplying power times time. The power is 60, time is 600 seconds, so we get 36,000 joules. This is the energy. So we can use this energy, 36,000 joules, to be equal. Obviously, the energy that was lost by the heater is the energy that was gained by the water, assuming that there were no other losses of energy. So the energy lost by the water is the same energy that was gained. No. The energy lost by the heater is the same energy that the water gained. So in that particular case, therefore, we say 200 times C times the change in temperature, which is 28.2. So this gives us C to be 36,000 divided by 200 times 28.2. Then we are going to get 36,000 divided by 200 divided by 28.2. So this is the value that we must get, 36,000 divided by 200 and by 28.2. Remember that we converted this to 0.2, so we must divide the figure, we must multiply this figure by 100, so times 100, so that we get this total. Okay, Then when we leave it as it is, and then we wait for it to be used in the next question. Can we move on to the next question? We have to use this in the next question. Calculate the specific heat capacity, and that is what we've done. Then to the 200 grams of water at 48.2 and 100 grams of water at 20 degrees C, calculate the final temperature. I think we'll be able to sort out this matter in the next session. Let's wait and see how the next session goes. Thank you, viewers, for being with us throughout this period. We'll be able to continue with these questions as we proceed in the next session. Thank you so much for being with us on this MTN Telescope. And thank you to all of those that have sent comments to this program. Thank you so much. See you in the next session.
Tiende pamoja ni mtima umo. 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 Tiende pamoja ni mtima umo.
So we'll pick it up from